Hi, Brian, Paul, Tracy, Kathleen. I just wanted to remind you that all of you are unmuted on my end, so you might want to mute yourselves until we get started. I think somebody is not on mute. And to everybody else on the call, hi, this is Jessica Rohde. I'm the web manager at IARPC. Thanks for calling in to the Arctic Digital Elevation Model Project, our first webinar of 2016. We're going to get started in about 8 minutes. And I just wanted to let everybody know that you're all muted by default when you join this webinar in order to cut down on the background noise. So if you have any questions for me, please use the WebEx chat feature, and it'll be found under, if you move your mouse to the top of your screen where there's that green bar, you should see the chat panel up here. And we'll get started in 8 minutes. Thanks. Hi, everybody. This is Jessica Rohde. I'm the web manager at IARPC Collaborations. Welcome to the Arctic Digital Elevation Model Project. We'll get started in a couple minutes here. I just wanted to let everybody know that you are all on mute when you enter this webinar, except for our panelists. And if you have any questions, please use the WebEx chat function to send a private chat to me and let me know if you're having any issues. And we'll get started in a few minutes. And as a reminder, Brian, Paul, Tracy, Kathleen, The four of you are not unmute right now, so you might want to, in fact, please mute yourself so that we don't hear your background noise. Okay, Tracy went to mute. Paul, Brian, Kathleen, are you guys hearing me? Maybe they stepped away.
So it doesn't sound
I'm here, but I'm on mute.
Oh, okay. Are you
I'm here
muting?
also, and I'm on mute.
Oh, okay. Okay, then maybe it doesn't show me when you're muted on your phone. But as long as you have muted through your phone, then that's good. So thanks, and we'll get started in a few minutes, everyone. Martin, this is Jessica Rohde. Can you hear me? Martin Jeffries?
I can hear you. Yep,
okay, great.
I can hear you. Can you hear me?
Yep, I can hear you, and I've unmuted you, so now you should be able to control your own muting.
Okay, thank you.
Yep. And hello, everybody else who's just joined us. This is Jessica Rohde. Welcome to the Arctic Digital Elevation Model Project. We're going to get started in a few minutes, but I wanted to let everyone know that you are on mute by default so that we cut down on background noise. And if you're having any issues, please use the WebEx chat function to get in touch with me. And you can find that by hovering in the top center of your screen where the green bar is and clicking the chat panel. And we'll get started in a couple minutes. Thanks for joining us. Martin, did you go to mute?
Oh, sorry. Can you hear me typing?
I think so, yeah.
That's good.
Hi, everybody. This is Jessica Rohde. I'm the web manager for IARPC Collaborations. Thanks for joining us today. This is the first of our webinar series, the first in 2016, and it's on the Arctic Digital Elevation Model Project. So thanks for joining us. I wanted to let everybody know before we begin that everyone except our panelists is on mute by default. And that's to help us cut down on background noise because it's we already have 68 people joining us, so it tends to get a little noisy if we don't do that. So if you have any technical difficulties or if you have any questions for the panelists, I encourage you to use the WebEx chat function. And you can find that by scrolling your mouse over the top center of the screen where the green bar is showing and clicking on the chat panel. And we will be saving our questions for the end of the presentations. But you can feel free to type your question into the chat function and I will relay it to the presenters in the order that I receive them. And I think I'll give it just a minute or two since we're getting a large influx of attendees right now. And then I'll be turning it over to Martin Jeffries, who is our host for today. If you are having issues on audio, please chat me and let me know and I'll see what I can do to help you. And I'm going to go to mute for another minute or two while we wait for more of us to join. Thanks. Okay, hi again, everybody. This is Jessica Rohde. We've had a few more people join us, so sorry for these repetitive announcements, but I wanted to make sure that everybody knows that this is the Arctic Digital Elevation Model Project webinar. Thanks for joining us. And two, that all of the attendees are on mute by default so that we cut down on our background noise. There are 85 people on this call, which is a really great turnout. Thanks for joining us. But if we had you all able to convey your sound, it would be quite a mess. So you're all on mute, and if you need to get in touch with me with technical difficulties, or if you'd like to ask a question for the presenters, please use the WebEx chat function. And you can find that under the green bar on the top center of your screen. There's a button that says chat. And if you type your question there for the panelists, I'll relay them to the panelists at the end of the call. The other thing I wanted to let you know before I turn the webinar over to our Master of Ceremonies, Martin Jeffries, you'll see on your screen, if you're connected to WebEx, a link to IARPC collaborations. And we are hosting this webinar, and we also, in addition to hosting webinars on Arctic science, we have a website that allows both federal and non-federal Arctic scientists to communicate and collaborate on the research that they're doing. And our teams and our member space on the website is open to anybody who can contribute to the Arctic research in our 5-year plan. So I encourage you, if you don't have an account on our site already, to go to that URL at the bottom of the screen. It's iarpccollaborations.org/request-account. Or get in touch with me and I can tell you more. Okay, now we're up to 92 people, so I think it's time for me to turn it over to Martin, who will introduce our panelists. Martin, are you there?
Yes, I'm here. Thanks, Jessica.
You're welcome.
Well, good afternoon, everybody, and welcome, as Jessica mentioned a moment ago, to the first of our IARPC collaborations webinars of 2016. I'm Martin Jeffries. I work for the Office of Naval Research in Arlington, Virginia, where I'm an Arctic Science Advisor and Program Officer for Arctic and Global Prediction. And I'm very pleased today to be able to introduce this webinar on the Arctic Digital Elevation Model Project. And this is a really interesting collaboration among a number of entities: the National Geospatial Intelligence Agency, the United States Geological Survey, and the National Science Foundation through an award to the Polar Geospatial Center at the University of Minnesota. So 4 parties, and we have a speaker from each of those entities, well, actually 3 of the 4 today. And so I'm very pleased to introduce, in no particular order of importance, it's just the order on the flyer on the website. First, Paul Morin of the University of Minnesota Geospatial Intelligence, the Geospatial Polar Geospatial Center at the University of Minnesota, Tracy Fuller from the US Geological Survey, and 2 people from the National Geospatial Intelligence Agency, Brian Bates and Kathleen Williamson. I don't know who's going to be the first speaker, so I leave it to you to take it away, please.
Tracy's going to be going first. So Tracy, I'm passing you the ball. And if you're connected to WebEx, you should be able to see Tracy, his face on the participants panel. Tracy, are you on mute still? I'll unmute you. There you go. How's that?
All right. Is that working now? Can you?
Yep, we can hear you.
See and hear? Okay. I'm very pleased to be able to offer a little background on the Arctic Elevation Project and an additional project that USGS is focusing on in Alaska regarding elevation collection.
Tracy, sorry to interrupt you, but I don't think you're sharing your desktop right now. So you might need to click the Quick Start panel in the top left and then the Share My Desktop button. There you go.
Okay, thank you. Okay, are we good now?
Yes.
All right, thank you very much. I'm very excited to be able to share some background information on the Arctic Elevation Project and how that is working, some status on that, and also a statewide collection that USGS is involved in of an additional elevation product over Alaska in particular today. The exciting news here is that incredibly high-resolution elevation data is being created for the first time over the entire Arctic, 60 degrees in north, and all of Alaska and Greenland. And Dr. Paul Morin will tell more about this later. All of this data will be available to the public for free for unrestricted use. So very exciting opportunity for computer modelers, GIS practitioners, and scientists around the world, something that just is unprecedented. So glad so many people were able to join today and listen to some of the activities that are going on. I was asked to give just a short introduction to a digital elevation model, or DEM. It's a representation of the terrain, the surface of the Earth or a planet or the moon, and it's how do you get the terrain into a digitized format for use in a computer. One very common structure is a regular grid of elevation heights. That's demonstrated by this graphic that shows some heights, and then each point in this regular grid would have an elevation associated with it. The ground distance between points is called the DEM density or resolution. And for example, over the Arctic, there is 1,000 meter data available, and some agencies have access to 100 meter data. Many of our, within the United States, 30 meter and 10 meter are common. But for Alaska and the rest of the Arctic, it's been very, the resolution has not been that great, and if we're moving to an 8 or a 5 or a 2 meter resolution Arctic-wide. It really expands the use of the data. Some common uses of digital elevation models, or DEMs. Just wanted to cover this real quickly. Many years ago, some of the earliest applications were to use these grids of elevation points to develop contours and shaded relief images for use on maps. And then some algorithms were developed to develop slope and aspect models that could be used to identify other features on the landscape. And then the use has exploded over the ensuing years in GIS applications and computer models and simulations. These are just a quick list of some of the ones that I've either worked on or know of other people working on, and the uses are really expanding daily as people are finding ways to use these digital data. Natural resource management, a lot of wildfire forecasting is done. Glacier studies and climate modeling is a big one that people are using elevation data for now. Flood and tsunami inundation modeling, line of sight or visibility, where do you put your cell tower? That's a big one. Coastal erosion forecasting, if you really know the elevation and what's happening along the coast, it can help define be an input to models. Drainage flow accumulation is one that we use at USGS, and aircraft safety and rescue operations are some good examples of how a digital elevation model helps in all of these cases, and many, many more. I wanted to explain very quickly the difference between two common DEM subtypes. One is a digital surface model that shows tops of trees and structures so that you can get some characteristic of what's happening on that level of the ground. Sometimes you might hear this referred to as a first return of information. And then if you have a sensor that can or you use some technology or techniques to remove the structures and the vegetation to get down to the bare earth, that's called a digital terrain model. And these two graphics just are a quick depiction of what you might see looking at a graphic of that, and how the pictures on the right show the surface that you might be looking at. There are many modern elevation collection techniques. Here are a few of the major ones, two that we're going to talk about today, and then one that many of you may have heard of or are working with. Airborne satellite or stereo imagery can be used. The position of the sensor is known. In this depiction on top, you see a satellite, and then there's a common point between the two images that can be used with some calculations to derive elevation. Airborne or satellite radar is another technology common in use. An active radar wave is sent to the ground surface, and then the reflection from that is received on the sensor on board the aircraft or the satellite. Airborne LiDAR is becoming a very strong program now. A light pulse is sent to the earth, and the reflection returns to the aircraft, and based on the timing of departure and receipt of that beam back at the sensor, you can calculate the distance. So with that background, I just wanted to present just a little bit on an Alaska radar elevation project that the USGS is monitoring and working with partners. This is under the USGS supervised or oversight 3D elevation program, or 3DEP if you've heard of that. This program, USGS is working to develop partnerships with states, federal agencies, private vendors, and others to collect enhanced elevation data over all of the conterminous U.S., Hawaii, Alaska, and the U.S. territories. For Alaska in particular, because of the size of the state, We are collecting this radar data, and the specific radar sensor that we're using is called Interferometric Synthetic Aperture Radar, or IfSAR. USGS is supporting this collection to meet requirements that were collected through the Alaska Statewide Digital Mapping Initiative group, and their requirements were for a 5-meter elevation grid or better. They wanted both a digital terrain model and a digital surface model delivered at least 3.6 meter vertical accuracy, assessed and checked at that level. If we could deliver this, it would meet map accuracy standards for 1 to 24,000 scale mapping, and the state of Alaska wanted us to move from the older scale of 1 that didn't show as much detail to this 1 to 24,000 scale that was common in the conterminous United States. And at this scale, 20-foot contour intervals would meet the accuracy standard that the Alaskans were looking for. Along with the digital terrain model and digital surface model, we also collect an orthorectified, it means it's measurable and planimetrically is correct on the ground, radar image. So this is a pseudo image. It's based on the radar reflection intensity, very useful for delineating surface water features, and it's finding a lot of use helping control new imagery and elevation collects in the state. Another deliverable are the break lines. These are hand digitized lines that delineate ridges, valley bottoms, and riverbanks. A lot of scientists are finding use with these, and they're created to help correct the overall quality of the DEM and to make sure that water flows correctly over the digitized landscape. At USGS, we're finding these break lines very useful to update the Alaska National Hydrography data set. This is the USGS overseen product for surface water, and Alaska needs a lot of work, and these break lines over the life project of updating Alaska National Hydrography data set, we estimate will save us about 10,000 man-hours of labor. So that's a good product if scientists and others are interested in that. And finally, we're collecting over 800 GPS surveyed control checkpoints across all of Alaska. These XYZ locations are used by us to assess the IfSAR quality, but they're also proving very useful in assessing other imagery and elevation projects and improving the accuracy of those products. Where are we in this project? It's a very expensive program, estimated to cost $62 million over the life of the program from approximately 2010 to 2018. It's all purchased through volunteer contributions from the state of Alaska and federal agencies. And we're 62% complete. You can see the blue. That's where we fully funded. Data are available for download, or their last few cells that are in work right now. And we expect to collect this northeast quarter this summer when flight conditions are right for us to ensure that there's no snow on the ground. So we're looking forward to this collect to finish that off, at which time we'll be at 70% funded and in work. So with that background, there's another project that we're going to lead into now and discuss for the remainder of this webinar. In the spring of 2015, the Arctic Council accepted a proposal under the addressing the impacts of climate change element. During the U.S. chairmanship of the Arctic Council from 2015 to 2017, one of the initiatives that was selected that was accepted and approved was to work toward development and distribution of a pan-Arctic digital elevation map. We called it a map just to make it simple in case people didn't understand what we meant by model. But this proposal was accepted, and the requirements that we were trying to address were to improve public access to a high-resolution Arctic elevation data set, better than had ever been out there before, to provide a single point of access so people didn't have to go country to country looking for data. Also, the Arctic Spatial Data Infrastructure, this is a group that is representing the national mapping agencies of all 8 Arctic nations, were to coordinate on international support for the project. And the working group, CAF working group, the Arctic Council's Conservation of Flora and Fauna working group, would monitor progress and make sure things are on track. So that was back in the spring, in February and March, and the proposal was accepted and some initial work was started. And then President Obama announced in September of 2015 that the Polar Geospatial Center was going to be funded to create an Arctic-wide DEM. So this excited everyone. It's a very elegant solution to the original initiative language. And so we began working with Paul and making a link between the Arctic nations to support Paul in whatever way they could or they were capable of, Paul Moran and the Polar Geospatial Center, to help with this project. So USGS is involved coordinating this international support. We're organizing a series of workshops with the Arctic nation representatives, and we're interfacing between the Polar Geospatial Center and these nations to try to make things move along to help improve any way we can the product that the Polar Geospatial Center is creating. USGS is producing the progress reports for CAF that go on to the Arctic Council, and we're also coordinating some international requirements gathering activities. There will be an initial delivery of data, and then we're going to look at what could be done outside of the initial delivery to ensure that the quality and the format of the data and the resolution meets the needs of the international science community. The Arctic SDI, made up of the Arctic nations, they can do some things, and they're working on some things to help. They're providing control point data to help improve the DEM accuracy. Paul will describe that in more detail. They are reviewing data and reporting issues. They have some sample data, and so they're helping to improve the overall product technology there. After the data is delivered, some of the countries are actually going to edit using internal resources and create an improved national product for their individual nations. And we hope that we can then push those products out to the world also after they're improved using local resources. So with that, that's what I wanted to present as a start for this, and then turn it over to Paul. Thank you.
Thanks, Tracy. Paul, I'm passing you the ball.
Okay.
And you'll need to press the share my desktop button, and I will switch the camera over to your face. If I can figure out how to do that. Here we go.
Okay.
I think we still see Tracy, if you don't mind giving me 1 minute while I work on that. Darn. Sorry, everybody. This is my fault, not theirs. Well, why don't you go ahead, Paul, and I'll see if I can figure it out while you're talking. Sorry about that.
No problem. Thank you so much. It's a pleasure to speak to all of you today about this and a project that we've been working on so hard for so little time. I'm going to give you a background on this fairly unusual project. It's the joint effort from a number of people. the top three institutions from the Polar Geospatial Center, Byrd Polar, and Cornell are the primary groups that are actually producing this elevation model. Brian Bates and Kathleen Williamson are joining us from the National Geospatial Intelligence Agency, one of our very important partners that will they'll speak about their efforts in a moment. The Polar Geospatial Center, just to give you a bit of background, we provide geospatial support for NSF-funded polar science and logistics efforts. And so we're here to make science better, cheaper, faster, and safer through geospatial data. And we do that in any number of ways. We do it through maps, we do it from GIS analysis, and we do it with remote sensing data. And we have a fairly unique or just a very good relationship with the National Geospatial Intelligence Agency, where we receive a large amount of sub-meter commercial imagery. So this is imagery that is at a resolution of 32 to 42 centimeters for the entire area of both poles, so both the Arctic and the Antarctic. Can people see my screen yet, Jessica?
Yes, we can see your screen. We just can't see your face. That's the problem
okay.
I'm having.
That's no problem.
Yeah.
And so this image that we're looking at right here is a 32-centimeter image from the WorldView 3 satellite from Digital Globe that was licensed through NGA, and it shows McMurdo, Antarctica. And there are a few points here I want to make. Number one is all of this imagery is independent of logistics. We do not need aircraft. We do not need to send out a drone for this. The satellites are orbiting all the time. And since they're polar orbiting satellites, there is a lot of collection capacity at both poles. What we do is, we try to make polar science and logistics go much easier. And one of the things that we support is the Greenland Inland Traverse. So this is a traverse from Thule Air Force Base to Summit Station in the center of the Greenland ice sheet. And we, on a very consistent basis, make up both remote sensing mosaics and maps, but we also make elevation models of all of these areas. And so this is an example of one of the analysis products that we give back to both NSF and the contractors that are pulling supplies to Summit Station. What we're looking at here is a shaded relief image of elevation data as Tracy described it before. And overlain on top of it is the route of the Greenland Inland Traverse to Summit Station. And this elevation data is good enough that we can draw a profile along this route, and on this profile we can actually see what the elevation is at any one given point, but more importantly we can tell them the slope. So if they want to move this traverse, we can actually tell them whether the tractors can go up that hill or not. We're doing this piecemeal. Here's a shaded relief image again of an outlet glacier where the Greenland ice sheet is squirting out a fjord in western Greenland. We were getting large numbers of requests from scientists that wanted this kind of data and knew that we could produce it. Here's another logistics hub in the Arctic for us. This is Kangerlussuaq Airport in central western Greenland. We started to produce this data, and it started to look very, very similar to LIDAR, to IfSAR. And we started to consider what would it take to take this stereo imagery that NGA was providing and just do the entire Arctic. And so probably about 12 months ago, Brian Bates is on this call with us, and I and a few of our colleagues started putting together a white paper just to analyze what it would take to produce a circumarctic elevation model. And we came up with a few points. We needed additional stereo imagery from NGA. We needed increased networking. No longer really is mapping, if you go this route, mapping is no longer an aircraft-bound problem. It becomes a storage, networking, and compute-bound problem. We need industry partners because we're a small project. We only have a few people on this. We don't have all the resources for every aspect of this project. We needed high-performance computing. That's one of the secret sauces here in what we're doing. And we needed additional funding for staff and storage, and that's provided by the NSF Arctic Research Support and Logistics Program. And so the first thing I want to remind everybody that we know of on this call is the Arctic is big. It's several times the size of the lower 48. We're talking about, with fewer than a dozen people, providing 2-meter posting elevation data for an area that's 3 or more times the size of the lower 48 in the United States. And so our goal here is to produce a publicly available, high-resolution digital surface model of the Arctic during the U.S. chairmanship of the Arctic Council using digital globe stereo imagery licensed by the National Geospatial Intelligence Agency. Did you want to speak, Brian, about any of this?
Yeah, can folks hear me?
Yes.
All right. So what I would just like to do to the folks is introduce the National Geospatial Intelligence Agency, or NGA. We are a Department of Defense combat support agency, and the reason that the way that the National Science Foundation and Paul Marin and his Polar Geospatial Center and NGA came together was after its creation, NGA was chartered by the Department of Defense to procure commercial imagery for Department of Defense missions, which includes map making, and my colleague Kathleen Williamson will talk a little bit about that in a minute, including digital elevation models. And the commercial imagery industry here in the United States, as folks probably have gathered or knew already, that over the past decade and a half it has expanded rapidly in the number of satellites it has and in their fidelity or resolution of the imagery that they produce. So it's become more high resolution, more mature, and we're better able to utilize it for several product lines, including this one. Also, the satellites all fly in a polar orbit, so each satellite is exposed to the poles pretty much on the hour, 24 hours a day, which means they have a high capacity for collecting satellite imagery, weather permitting, over these areas. A few years ago, it was determined by our folks here at NGA that we had the authority to provide this imagery not only to the civil community but to federally funded scientific and academic organizations, and that's how we came in contact with Paul. And as Paul mentioned, we've been working together now for about 6 years, and at the time that we met, I was in charge of the commercial imagery collection branch here at NGA, and we designed these ever-increasing large-scale polar collection activities, and we moved into stereo shortly after the first year, I believe, and began this collection. Earlier this year, President Obama signed an executive order that required the different federal agencies, including USGS, to coordinate their Arctic activities. He set up an Arctic Executive Steering Group that Tracy mentioned earlier, and then the white paper that Paul mentioned sort of all came together in the spring, where we talked about how could we contribute to the current administration's emphasis on polar activities, climate resilience, and so on, and that's how this project came about. And then NGA supported the President's trip to Alaska, where he announced several of the projects, including this one, when he became the first president to travel north of the Arctic Circle. That's all I have, Paul.
Okay, thank you, Brian. And so we're using, Digital Globe at one time had 6 satellites. We're using 3 of them, Worldview 1, 2, and 3. imagery. So this imagery is 32 to 42 centimeters panchromatic resolution. So that's the size of the pixel that you can see on the ground. So compared to Landsat, this is something like 900 times the resolution of Landsat. One of the secrets here to the success of this project is the NSF capacity for high-performance computing, and I can't stress that enough. The computer that we're using for this is called Blue Waters. It's at the National Center for Supercomputing Applications at the University of Illinois, Champaign-Urbana. This is the 16th largest computer in the world. Where your computer on your desk right now that you're using to view this presentation, it has approximately 4 cores. Those are each processing units in your CPU. This computer has about 750,000. This is a very, very large computer, and we've received a startup allocation to be able to get this going. They have petabytes of storage, and in this case, 26 petabytes, so that's 26,000 terabytes of storage on this. We have very, very fast networking to Minnesota, so we can move large amounts of imagery back and forth, and it's an NSF resource. This is the kind of thing it can produce. So this is a test that we just produced for the state of Alaska. It's 8-meter posting, so each elevation data point is 8 meters by 8 meters. This doesn't yet include all of the imagery that we started to collect this season. We're just beginning to process that, but it just gives you a sense of the scale that we're working at right now. The North Slope is very easy for us. It's very, very high latitude. There's not a lot of competition for the satellites in this area. Anywhere that you see a little bit of white, we just haven't produced elevation yet, and either the data, is being moved to the supercomputer, or NGA is adding additional tasking to fill those holes. This is around the Kuparik watershed. NSF contributes to a facility up here called Tulik. There's a long-term ecological research project up here. This is a seamless single-source elevation model for the entirety of that study area. We can also do very, very remote islands. This is St. Lawrence Island off the west coast of Alaska. Size is really becoming an interesting issue here. This is Greenland. It's a very, very, very important topic for glaciologists, for sea level rise, for any number of issues. On the right is our current draft of an 8-meter elevation model for Greenland. On the left is a zoomed-in area in southern Greenland. You can start to see the individual glaciers, outlet glaciers, flowing from the ice sheet into the ocean here. Canada, here's the country of Canada. Baffin Island is done. We just didn't put it in. Many of these holes have been filled already. Here's Ellesmere Island, including some of the last ice sheets, ice caps in North America. Here's Stephenson Island, Nunavut. This is a drumlin field on the end of an island. This is a glaciologist or a geomorphologist's dream here. This is Barnes Ice Cap, Baffin Island in Nunavut. This is the last gasp of the Laurentide ice sheet that covered many of us 21,000 years ago. So this now is about 100 kilometers wide, and it's melting as it's going. Here's Kamchatka. The way we define the Arctic is 60 degrees to the north, all of Kamchatka, all of Alaska, and Greenland. That area in red on the right is on the left of the image. You can see the individual volcanoes there and many of the lava flows. And just to show that we're completely independent of aircraft logistics, this is the northernmost points of Novaya Zemlya in Russia. That little red box on the upper left is the absolute end of the island, about as far north as you can get, and you can see the ice cap and the geology there. We're already passing this data to many of the partners that Tracy talked about. One of the early partners were the Icelanders. They were clamoring for this data, and Icelanders have an advantage over many of the other Arctic nations. Number one, they're small, and number two, they have access to everywhere. And so we produced a 2-meter posting elevation model of about 80% of Iceland, and the Icelanders went in and compared it, in this case, with their uniform elevation model that they have for Iceland, and then they put our elevation model over top. So this is 30-meter posting. This is our 2-meter posting elevation, and you can see roads going through the middle of this image here, and you can see some wonderful, wonderful geology in there. Here's another one. This is actually one of my favorite examples that they gave us. This was their uniform elevation data that's of the same quality across the entire country. This is Reykjavik before, and this is Reykjavik with ArcticDEM. You can see all the houses, you can see moraines, you can see the roads. We have time here. Brian talked about we started to affect the collection. We started to influence the collection about 3 or 4 years ago, and we started to influence it in places that are key for American science. In this case, Columbia Glacier. What this image shows is that we had a stereo pair in 2009 and another one in 2013. We created 2 high-resolution elevation models, and we subtracted them. And what this shows is anywhere that's purple basically didn't change. That's the rock. When you start getting into the yellows, the reds, and the really dark reds, you can see that we lost up to 150 meters of ice on that left branch of Columbia Glacier. Here's another brilliant application for the elevation model. This is from Ben Crosby at the University of Idaho. He's been watching thermal karst collapse in western Alaska for almost a decade now, and you can see the picture of the collapse in this inset picture here. And so what he has been doing is going in and measuring it every few years to see how the whole slump has been evolving. And so what he's interested in is how each stage of this moves and then is stored, moves and is stored, moves and is stored, moves and is stored. And so before ArcticDEM, he would have to go out there and he would start collecting data. In this case, this is an interpolated initial surface. He would draw a line along this, and he would make a plot of this is the profile along that elevation. He would then go in with aircraft and create elevation with other technology. This is structure from motion in 2004, 2006 it was structure from motion, 2007 it was actually surveying on the ground with a total station, 2009 it was surveying on the ground, and on the left you can see each one of these profiles as time goes on, so you can see the slump retreat. 2010, he's surveying it by hand again. Then he has some ground scanning LIDAR. He used it in 2011. 2012, we started to get stereo from NGA, stereo imagery. We were able to create these elevation data sets. So here's a DEM for 2012, 2012 again from LIDAR, 2012 again from stereo DEM, in 2015. And so you have the entire history through a series of differing technologies, but now that we know that the ArcticDEM works, we can simply just repeat that stereo each year to complete his time series. Here's another one that we ran across by accident. So when the stereo is collected, you often get stereo in the same place but in different times. So we have one stereo pair here on the left that's from 2012 and another one from 2015. When we were creating the first test of elevation in Siberia, we created elevation in 2 places. These 2 elevation models overlapped, and the first thing we did was we subtracted them. And so what we have here is elevation from a difference of 3 years subtracted. And if you look at these blue areas, those are areas of clear cuts. This is the middle of nowhere in Siberia. You can see that these clear cuts are a few hundred meters across. And then we've also called out, you know, there's a vertical line here on the right. That road, or that blue line of trees, are trees that were removed for a logging road to get in and do those clear cuts. And so even on top of this, going to the next slide, not only can we tell that there were trees removed in these areas, we can even tell that in this clear cut, the trees on the east side were 20 meters tall, and the trees on the west side of this few hundred meter long clear cut were 12 meters tall. Here's another application of this data that is much more governmental and societal. Melissa Larson in the inset was an NSF-funded intern that spent 6 months here at PGC when we were formulating this DEM project. And she used the technology and the imagery from NGA to create models of most of the Greenlandic villages. And then she went and calculated the extent of the watersheds that drain into the lake that feeds each one of the 72 villages in Greenland. And so by delineating in this image, it's this red line, that's the extent of the area that drains into this lake. Once they know that, they can protect this area so that the village doesn't put any garbage, petroleum, or especially in Greenland, dogs in that area, so that they can protect the water quality. We need to talk about accuracy. Without any type of ground control that Tracy talked about, we get about 4-meter errors here. And so that can be controlled for. That's also pretty close to within the error Tracy was talking about for his IfSAR project in Alaska. Also, if we use ground control, we start seeing errors on the order of 20 to 35 centimeters. And so, for example, that's using LIDAR by NASA over the Greenland ice sheet. There are limitations. This is a surface model. We are never going to see bare ground with this. The satellites are optical. They see trees. They don't see underneath trees. This is also optical imagery from orbit. We have to be able to see the ground. We can't see through clouds. We can't see through blowing snow. There are all kinds of issues with that. And also, once we produce a mosaic, a collection of all these different DEMs together, it will be a mosaic of imagery and DEMs from a number of seasons over a number of years. But there are certainly strengths to this. There's high collection capacity. We can go in and we can fill holes. We can repeat where there's bad data. Collection continues while the sun is 7 degrees above the horizon. So in certain southern parts of the Arctic, we can collect for as long as 9 or 10 months a year. The DEMs can be repeated. So you can start to see differences in the elevation because of thermokarst collapse, because of trees being cut down, because of other things changing. And one of the interesting aspects of this is as the software and the ground control improve, we can improve elevation models that were acquired from stereo imagery that was collected in the past. Also, this is a surface model. We can measure vegetation. We can measure it like I was showing in Siberia very, very accurately. No logistics are required. Where Tracy's project will provide that digital surface model, it's $62 million. Our project is about 2.5. So here's the production status. Green, we processed 8 meters, and we're now about to process all the way to 2 meters. Yellow, we have half of the imagery processed to 8-meter posting. In blue is we're currently processing the first round, 50% of the imagery to 8 meters. We have partners. NGA, National Science Foundation, USGS, and then we have industrial partners, Esri and Google. These are all absolutely critical to this success. If any of this changes, this project would not succeed. But the project is the partners are all really contributing their part, and things are progressing really well. I just want to end this. I have a few images that aren't in the PDF that I sent but are worth looking at. This is one of the most astounding projects I've ever been involved with in my career. Every morning as the elevation is coming off the supercomputer and we're looking at these tests, I've never seen places like this. Just this image that we're looking at here, it's meandering rivers and riparian vegetation in central Alaska. This image is just an erosional surface in western Alaska. This image is Point Hope. So this is one of the communities in Alaska under threat. And you can actually see the grid of houses there on the sandbar on the left. And so I want to really thank you all for your time, and I'd be happy to take questions.
Thank you so much, Paul. I wanted to remind everybody that you're on mute right now, and to ask a question, you'll need to use the chat feature, which is found under the green bar in the top center of your screen. There's a button that says chat. I have a couple questions that were sent to me already. Is somebody speaking? Is that Martin?
No, it wasn't me, it was somebody else. But please, I encourage anyone to ask your questions.
Okay, so the first question I received is for Tracy from Eric Holloway. And Eric wants to know, how does the IfSAR affect NHD Plus for Alaska? Is it now on a faster track? And Tracy, you're still on mute right now.
We have a really good test case where several partners, we were able to collect funding through several federal agencies and support an update, a very high resolution, accurate, high density update over the Matsu Basin. So that was like our test pilot for that. IfSAR was used to help improve that data. So we're hoping as Paul's data becomes available, as the IfSAR becomes available, and as we put additional funding into the core NHD data set that needs to be improved, then that will be able to then support the NHD Plus effort. So yes, I believe it will accelerate it. We really need to find the resources now to accelerate the actual updating. That Matsu Basin was really incredible. We updated, the partners were able to update. They added almost 10,000 stream segments. The linear mileage was really incredible, and the improvement of the accuracy just makes it really viable to do the NHD Plus calculations and create that data set. So yes, I think that pilot shows where we're going to be able to go in the future.
Thanks, Tracy. The next question is from Dennis Felixson. I apologize to anybody whose name I don't pronounce right. And his first question is there a plan to use GCPs in the creation of the ArcticDEM?
Yeah, this is Paul. There definitely is, and right now we're producing the elevation, you know, that's purely a high performance application. The next step after that is created is to apply ground control points, and so we're in a mode right now of collecting ground control from anywhere in the Arctic. So we're talking to all the participating nations. We're collecting whatever LIDAR is available, and that will be applied to the mosaic.
Thanks, Paul. One more question from Dennis. what will the strategy be for using images from different seasons? In other words, will every available image within a pixel be used, or will there be some sort of prioritization to use images from the same season?
Right. So we're delivering two things. One is a mosaic of, a best quality mosaic of all the different years and different seasons. And then we're going to deliver the individual strips that contributed to that mosaic. And we're still formulating exactly what the strategy is for mosaicing. I would suspect that it's something like most current elevation first, and then preferentially choosing certain seasons. We haven't exactly chosen that yet. But also, one of the interesting aspects of this is since we're also distributing the individual strips, individual users can mosaic that any way they want to make a 2013 or 2015 a spring mosaic, that kind of thing. And so we expect users, whether they be individual scientists or a country like Iceland, to be making these products themselves after we release the strips.
Excellent. Okay. The next question is from Dean Gesh, and he's asking, oh, sorry, go ahead. Was that Brian? I keep hearing somebody trying to speak. Sorry. Okay, so Dean Gesh asks, will there be a mask that indicates the date of the images used to derive elevation on a per pixel basis?
That's the current strategy, yes.
Okay. A similar question, Adrian White asks, what range of years was used to create the DEM?
There was stereo collected pre-2012, but it was not in very large volume. Most of this data is 2012, 13, 14, 15, 16.
Okay, and then two similar questions from two different people. When will you be releasing the product, and more specifically, any guesstimate on the Alaska 2-meter product, when that will be available?
The strategy right now is to release Alaska at 2 meters, both the strips and a mosaic, this spring.
Excellent, okay. And then Kang Yang is asking, are any cross-validations conducted, for example, comparing the accuracy of WV DEM and InSAR DEM?
InSAR DEM is commercial, and we don't have access to that. We will certainly compare it to the USGS IfSAR, and we will compare it to others. And so that's, right now we're in a production phase. We'll get to the ground control phase and the mosaicing phase, and then we'll do, we'll have a validation phase along with that.
Great. Okay, more questions are coming in, so I'm just going to keep going. We've got, Adrian White is saying she has GCPs collected from Northern Ellesmere Island. Can she contribute these? Also, Canadian survey points, have they been incorporated as GCPs?
You're our hero. Right on the screen right now is Mike Cloutier's email address. Email him immediately, and we'd be thrilled.
Excellent. I think you answered this, but is Greenland going to be released with everything at the same time?
It's a two-stage release. We promised Alaska this spring, and then we promised the Arctic a year after that. And so right now, I believe we've got 3 or 4 Greenlanders on this call right now. The idea is apply as much of the ice bridge and ASIAC and some of the Danish ground control data. But right now we're really, really focusing on producing Alaska at 2 meters and making a good product.
Great. Okay. Well, One more chance we're about at the hour. The last question I've received is, where will the DEMs be downloadable from? But please, if you have any more questions, type them in the chat function now. Otherwise, we'll wrap up here in a minute.
So PGC will provide a mechanism to download this, as well as NGA. Also, Google has expressed interest in distributing data through Earth Engine, and we're currently discussing with Esri exactly, how we will work with them on distribution of this data. The data is, we expect to not be restricted. So we're hearing that various people want to distribute it in different ways for different purposes.
There's a couple more questions, but we are at the hour. If you're able to stay on, I'm happy to relay a few more. Okay, hearing no objections. The next question is from Carl Brix Zinglersen, and he says, the ArcticDEM project is marvelous and will be unbelievably important to Greenland. How are coastal areas and water bodies handled, changing tidal areas, icebergs, etc.?
That's an interesting question, and a partially loaded question. The technique we're using, the photogrammetry technique, does not work on water because waves move during the 45 seconds that it takes for the two images to be collected. And so that generally becomes a void. That's in the ideal case. In the Arctic, you have lots of sea ice, so you actually can create elevation for the sea ice next to the land. Accurate coastlines are very, very important, and we're now getting the best possible coastlines for many of these Arctic nations right now, and that will be applied to one of the DEM products. We imagine that the DEM will also be more accurate than many of the existing coastlines, and so we may just have a product that has no coastline applied at all. The other question he had was about tides. We're actually getting to a point now with elevation models that tides are an issue. There are certain places in Canada, Scandinavia, just all around the Arctic where you can see water, the tide go out many tens of meters, if not hundreds of meters sometimes. And so we just have to deal with it. The satellites generally go over between 10 and noon every day, and so it depends on what the tide situation is on that day, on that time. And so it's one of those interesting questions we're starting to run into.
Yeah, that is really interesting. Okay, two more questions, and I think we'll have to stop after that. Luke Copeland is asking, will the original worldview images be available in addition to the DEMs?
No, and that's a very good question because the worldview imagery is licensed for U.S. federal purposes. This DEM project is a derived product that's no longer bound by that copyright. The imagery itself cannot be given to other users, though the imagery can be requested by agencies and researchers who have an access point into the commercial imagery program, but we cannot give away that imagery for this project. This is an elevation model project.
Okay, and one final question. Do you plan to release derived products such as flow networks, break lines, etc.?
That's also a very good point. This project is all about high-performance computing, storage, networking, satellite capacity, and cleverness and automation. It's not about manual labor. And so we will not produce anything that requires big legions of people to be able to edit data. We're doing everything possible to automate that, but we don't have, you know, the dozens and dozens and dozens of people it would take to produce that kind of derived data. We're expecting, though, that once we release this, there will be a number of people that will start making their own value-added products. And we're already seeing that from both Natural Resources Canada to the Icelanders and the Greenlanders are already looking at creating their own value-added products.
Thanks so much, Paul, Brian, Tracy, Kathleen. I'm sorry we didn't get to hear from you. I want to encourage everybody to get in touch with the speakers individually to ask your questions. There are some more that are still coming in, and I'll let our Master of Ceremonies make some closing remarks now. Martin?
Well, thank you, Jessica. A quick hello to Luke Copeland and Adrienne White in Canada, my fellow Ellesmere Island researchers. It's good to know you're on the line, and I hope you'll continue to participate in IARPIC collaborations events. But more importantly, I'd really like to thank the speakers for telling us about this fantastic project. This is a remarkable product, and it's just amazing to see it. You know, as a long-in-the-tooth Arctic researcher who has worked in the Canadian Arctic with ancient topographic maps that's totally inaccurate, to see this product is going to be a great service just to people doing field work that requires great accuracy for navigating around and whatever. But I'm sure there are uses for this product that haven't been thought of yet. And the sooner it's in people's hands, the sooner we will see those innovative uses. So congratulations to the speakers for this amazing achievement. And it's not complete yet, of course. There's more work to be done. But so far, it is a remarkable achievement. Thank you for agreeing to give this presentation today. I think you've done a great service for IARPIC and getting the word out in this way to raise awareness of the product. And I wish you good luck with the completion.
Thank you, Martin.
And thank you to our audience. We have well over 100 people online, which I think is by far the largest IARPIC webinar audience. Thank you, everybody, for joining in. I think it's a testament to how important this product is.
Oh, this is Jessica Rohde. Just wanted to chime in one more time and encourage everybody, if you're interested in this webinar or future webinars or collaborating with other Arctic researchers, please request an account on our member space. The URL is showing at the bottom of the screen, iarpiccollaborations.org.